So let's keep going. Yesterday we were talking about the about methods of parameter estimation, and in particular the method of maximum likelihood. And once you construct an estimator, you would like to know if you were to repeat the experiment many times, how widely distributed would those estimates be? And so that was given by the standard deviation of the estimator. And we had a formula for the approximate, a good approximation to the variance of an estimator. So the variance of an estimator for a parameter theta was approximately given by 1 over the second derivative of the log likelihood function, evaluated at the maximum of the likelihood function, which is to say at theta equals theta hat. Statistical error. About the estimator, so I'll expand this. About theta hat. All right, so this is going to be log L of theta hat plus first order term plus something like this. And so forth, but if I just go to second order, so this here, of course, is by construction the maximum of the likelihood function, because that's how I've defined theta hat. And then because I'm at the maximum, of course, this term here is 0. Right? And then here in the next order term, the second order term, I have the second derivative of the log likelihood function evaluated at theta hat, and I can relate that to the variance of the estimator. I'll call this sigma theta hat squared. That's just another notation for the same thing.
So theta hat is the maximum likelihood estimator, not the
That's correct. Here I'm talking about the maximum likelihood estimator. So I've defined it in that way. Yeah. And so what we can do then is use this thing here to replace that term. And what I'll find is that this is then equal to log L max minus theta hat squared over 2 times this estimate of the variance, sigma theta hat squared. Voila. Okay, so that's the formula I wanted to get. I'll say approximate here. But in fact, the approximation is good in problems of practical interest. And so if you think about how this works, if we make a sketch of log L versus theta, I'm going to come up and go down. And so somewhere here we have the maximum, and that's where theta hat is. Now if I consider moving theta away from theta hat by 1 standard deviation, that is to say by 1 sigma theta hat, then this will go, then the log likelihood function goes down by 1/2. Okay, so if I make that term cancel that term, we get the following. So if I come down here to log L max minus 1/2, then that would correspond to moving theta away from theta hat by exactly 1 standard deviation. So it should be approximately symmetric. I could go to either side. And so that's the graphical method for determining the standard deviation of an estimator. You draw log L versus theta, you move theta away from theta hat until the log likelihood function goes down by 1/2, and that distance here then gives you the standard deviation of the estimator. And so that's just a simple graphical extension of this formula. What we'll find in general is that for a finite data sample, that log L is not exactly parabolic. And so you could find a situation that I'll draw it in sort of an exaggerated way. You know, maybe it's kind of like that. And so there's the maximum. And so you might find that when you carry out this recipe, that you get a different distance over here than you get over here. Maybe I'll call this this distance delta theta plus, and this distance could be delta theta minus. And so what do you do in that case? If your goal is to estimate the standard deviation of the estimator, then it depends on how accurately you want to estimate the standard deviation. Maybe you take the average. That would be a perfectly reasonable approach in many cases. In other cases, you might actually want to use this interval from here to here. So how could I write that? I'll say I'll take the interval from theta hat minus delta theta minus up to theta hat plus delta theta plus. And I will use that essentially as a way to report an asymmetric error bar on my measurement. And this interval is an example of what we call a confidence interval. At least it's an approximation to what I'm going to define as a confidence interval. And that also has a useful meaning in statistics, but it's I want to distinguish between these two exercises, the two problems. One is trying to determine the standard deviation, and that is one number. There's no such thing as a negative standard deviation and a positive standard deviation. The standard deviation is a single number that characterizes the width of a distribution. And this can be a good approximation to do that. If you get different values for the left-hand side and the right-hand side, I see I silly, that should obviously be called the minus one, and that should be called the plus one. Yeah. The interval, nevertheless, that goes from there to there has a useful interpretation as a confidence interval, and I'll define that more precisely in just a while.
So in practice, what happens when you have a skew is the cubic term is important?
Sorry, if you have this.
Well, in what situation do you get a skew? Is it when the cubic term is important?
Yes, exactly. And the way that arises in practice is that if you have a very small data sample. We did the example with the exponential distribution, right? And I said there were n measurements. And if you look in the slides of the lectures on the website, I did this once with 50 measurements, and it's pretty parabolic. And I did it again with 5 measurements, and you can see it's very noticeably skewed. So it's in the large sample limit, what will happen in general is that the likelihood function will become increasingly parabolic.
So you can show that the cubic terms vanish as
The cubic terms are, I'm not sure I'm going to go that far, but what happens is that in the region of what you're concerned with in the large sample limit is a region increasingly close to the maximum where the parabolic approximation is valid. You will still get deviations from the parabolic approximation as you go further and further away, but that would correspond to a departure of many, many standard deviations away from the estimate. Okay. Now, you can generalize this graphical recipe to the multi-parameter case, and here I'm just going to state the answer, and hope you will trust that the logic is very similar. But suppose you had a 2-parameter problem, but in fact this is the generalization to an arbitrary number of parameters. So let me just say theta I and theta j. There will be some point in that parameter space where the likelihood function is maximum. So I'll call that log L max. And then I can find the contour or the hypersurface in that space where the log likelihood function is less by exactly 1/2. All right, so I'll just write something like that. And again, what I would do is I would take the log likelihood function and expand it to second order in a Taylor series. And to the extent that the quadratic terms are sufficient, then this is an ellipse, right? Or in n dimensions, it's some hyper ellipse. So this is the surface of log L of theta equals log L max minus 1/2. Still 1/2. Right? That's what falls out of the mathematics, is the same number there. And so That, of course, is the estimator for theta I. That's the estimator for theta j. And then over here, you'll have some tangent lines, or tangent hyperplanes in the higher dimensional case. And to the extent that it's approximately symmetric, you can say that this distance here would give you the standard deviation of the estimator theta I hat, and correspondingly here for theta j hat, and so forth. And so that's the a very useful recipe for trying to understand what the how to get the standard deviations of an estimator. Now, I've here intentionally drawn this thing slightly tilted, and that tilt is an indication of a correlation between the estimators. And you can also derive the extent of correlation by looking at this plot. And I'll just write down the formula. This angle, how shall I write this? This angle here, I'll call that phi. And the tangent of 2 times that angle is equal to the, let's see, 2 times the, I hope I get the formula right. All you really need to know is that from the angle you can get the correlation. So this is given by 2 times the covariance of the 2 estimators divided by the quadratic difference of the standard deviations. Sorry, it's the difference of the variances. Voila. Okay, so that's actually what I wanted to pack into yesterday, so I'm not going to dwell on that too much. That finishes roughly what I wanted to say about parameter estimation and methods for determining the variances of the estimators. So maybe I should pause there for 10 seconds to see if there's questions. Because if not, I want to go on to the next main topic, and that is statistical tests. So within frequentist statistics, there's various ways of chopping it up, and one of the ways is to say parameter estimation, that's one part, statistical tests, there's another part, and we'll sort of bind the two together when we come to talking about confidence intervals. So let's go on. I'm going to erase this now. So next topic, frequentist hypothesis tests. Yesterday, I started by saying that a hypothesis was a statement that's either true or false. So I want to refine that definition a bit. So 1, it's some true or false statement. But now, more importantly, when I say that consider a hypothesis, that hypothesis has to provide a rule that gives you the probability for the data that you will be measuring. So it defines probability for data. So symbolically, I'll call that data x vector, as we've been doing. And so this has to give me then some formula for the probability of x, and I'll use this language of conditional probability. I'll put a vertical bar, so this sort of looks like probability of x given h. And so now you're thinking, that seems to imply that both x and h are admissible arguments to a probability function. Am I being a Bayesian? No, I'm just being sloppy in my notation, but this is the notation that is widely used. I don't necessarily mean that it would be meaningful to talk about the probability of h. H, if that's just a rule for a theory like the standard model or SUSY, that's not the outcome of a repeatable experiment. And so in frequentist statistics, I would not associate a probability with it necessarily. But with a just slight abuse of notation, I'm going to use the vertical bar anyway. Okay, so right. Very often, I should point out that very often this hypothesis will be characterized by some set of parameters, and so I could write, for example, p of x given theta, And what is implied by that is that this is okay, so I'll say that that means P of x given the hypothesis h and theta. So the parameters h are defined in the context of a particular model, and so the hypothesis in which those parameters lives is implied. Okay, and we've already said that if I view this thing as a function of the hypothesis and keep the data constant, that is then the likelihood of that hypothesis. So again, I'm going to be a little bit sloppy. This could be 1 or the x on the right. Sorry, yes. But just to emphasize, I'll sometimes write a vector if I want to emphasize that that could be a large collection of numbers, and then sometimes it's just a single number. That would be just a special case, and so then I'll drop the vector symbol. So it could be one or many numbers, and it could be continuous or discrete. All right, so very often in particle physics we're counting numbers of events, and so you'd have a discrete number of counts. The hypothesis is the rule that defines the probability for the data.
Yeah, but isn't theta exactly your prediction, or like the hypothesis want to guess if theta is a number? Like, isn't that essentially the hypothesis?
No, I'm not sure I get the question. Like I say again, the hypothesis is the complete rule that specifies the probability for the data. Now, I should be more exact in my vocabulary. We should distinguish between a simple hypothesis, and that would mean that this rule is completely specified, and this is then, say, fixed to a single number, right? And then I could have, for example, what I call a composite hypothesis. And then I would say that maybe I shouldn't write theta here. I should say that it's just a, let me just write it this way. Yeah. No undetermined parameters in a simple hypothesis. In a composite hypothesis, I would say that actually what I have is a family of rules, and the family is labeled by some parameter or parameters, right? But in the type of hypothesis testing that I'm going to get into just now, I'm going to focus on simple hypotheses. I'm going to insist that the rule for the probability be completely specified. Right. So now I need to define, I need more board space. So I'm going to erase this, but this was just a side comment. And I want to now define a statistical test. Yeah. It predicts probabilities for on a certain data space. So you have to define what are the quantities which constitute the data, but for every element in that data space there has to be a well-defined probability. Could be 0 for some parts, but yes, but and we know that we've seen that, for example, just in the example of an exponential distribution. If I, we were playing with this guy yesterday, that predicts this probability for the data, but if I change theta, I get something else, right? Yeah. Okay, good. Now, let me define a test. So to define a test, what I want to do is I want to make some statement as to the level of compatibility between the data that I get and a particular hypothesis. And in this type of test that I'm going to define, that statement will just be a binary statement. I will either accept or reject the hypothesis. And so what I want to do is consider a simple hypothesis H0. So that 0 means that that's the hypothesis that I'm going to test. I'm going to either accept it or reject it. And so often we use the language of the null hypothesis. The word null hypothesis tends to imply that this is the hypothesis in which nothing is happening, or say there's no new signal present. And in practice, that might often be the case. But that's not always the case. I'm just simply going to take the phrase null hypothesis to mean the hypothesis that I am testing. All right? And consider also an alternative hypothesis. I'll call that H1 for now, but there could be many alternatives in general. And so a different rule. And for now, put that on the back burner. We'll get back to the alternative hypothesis in just a bit. But I'm going to define the test now by defining a region of the data space called the critical region. I'll use a W. And this is in the data space, so X space. And the defining property of the critical region is that the probability to find the data in the critical region under the assumption of the hypothesis that I'm testing, H0, that should be less than or equal to a specified constant that I'll call alpha. It's always called alpha for some reason. And this is called the size, or sometimes called the significance level of the test. Right. So very often, so this is a pre-specified constant. So I should emphasize that. It is a pre-specified constant. In the sense that I give its value before I carry out the test. And very often we would just use some conventional value like 5% or 10% or something. It's supposed to be small. So formally, I want this to be a small number. Say 5%, we'll use that as our default. Right. And the idea is now the following. So sorry, before I go on to the main idea, I want to comment on this less than or equal to. I would actually prefer, in defining a test, to have an equal sign there, not a less than or equal sign. But if my data space has discrete values, like say it contains a number of events, then there might not be any particular subset of the data space whose summed probability is exactly equal to the pre-specified alpha, say 5%. So if I'm counting events, maybe the probability to have 0 or 1 is 4.7%, but 0, 1, or 2 is 5.3%. So I can't actually form a subset of the data space such that the probability is exactly equal to alpha. If that's the case, I take it to be the largest set of X space that I can find that doesn't exceed alpha. Okay. Right. Then next, observe the data. All right. You do the experiment, and you say if X is in the critical region, reject H0. Done. Okay. So that's easy. Why does that make sense? Well, you obviously you want to reject H0 if it produces an outcome which in some sense seems unlikely or uncharacteristic. And here I've picked this this critical region to only cover a very small probability, alpha, say 5%. And so it seems unlikely. That seems uncharacteristic in some sense that H0 should produce data in the critical region. And so that being small, if it actually happens, I say, that doesn't seem very likely. But of course, it will happen with a probability of alpha by construction, even if H0 is correct. Now, this is where, let's go back here. That seems incomplete. I hope you're thinking, that seems incomplete. Let's leave that for just a second. Yes? No, you observe now one point in X space. Yeah, so the result of my experiment is defined to be a point in this X space. Right? So here's my X space. the observed value of, so this leads to a single point, x observed. All right? No, there's one, it's one point. Right? I define this vector x to represent the set of numbers that constitutes the outcome of my single experiment. All right? And so, but the point is that the outcome of the experiment isn't just one number, it might be a collection of numbers. That's why I put this vector symbol. All components of the vector x. Well, the point is that let's suppose it's two-dimensional. Okay, let's suppose that it has x1 and versus x2, and so I define that to be my critical region. Right? If the point is there, it's in the critical region, and therefore I reject the hypothesis. Okay, so this is the data space. That's my critical region W. All right, and if I find the observed value, x observed, in the critical region, I reject the hypothesis. Right. Now, this region here, by construction, has a probability alpha for the point to land there if the hypothesis H0 is true. And the first thing that you might be wondering is, well, hang on, there's an infinite number of choices. Why did you put it here? I could have put it over here. All right, so infinite number of choices for location of the critical region W. So where do you put it? And this is where the alternative hypothesis comes into play. It is basically the role of the alternate hypothesis is to motivate the selection of the choice of the critical region. And the basic idea is you want to put the critical region where there is a maximum probability to find the data if the alternate hypothesis is correct. So let me suppose I just have a one-dimensional data space. All right, so let's suppose that it's just characterized by a single number x, no vector symbol, and maybe the probability rule under the null hypothesis is like that. And let's suppose that under the assumption of some relevant alternative hypothesis, it looks like that. And so you can imagine that, well, I could put the critical region over here, or in the middle, or on the right. But basically the idea is the following. Suppose we define the critical region over here. That means that that area, by definition, is supposed to be alpha. Okay? And what I want to happen is I want the data to land in the critical region so that I reject H0 with maximum probability if some relevant alternative hypothesis is the true one. Right? So if this guy is actually the correct hypothesis, I will more likely see the data over here. And this area here is called the power of the test with respect to the alternative H1. So if I had different alternatives, then that critical region would have different levels of power with respect to them. But the basic idea, so I should write this, is to put W so as to maximize the power So I'll say that this is the power. I sometimes use the letter m for power, and this is the probability to find the data in the critical region under the assumption of the alternate. So as to maximize the power for some relevant alternative, or maybe some set of alternatives. And so now you might be wondering, would it be possible to define a critical region that would have a very high power with respect to all of the relevant alternatives that might come into play? And that turns out to be impossible. This is something that was argued and debated in the 1930s by Neyman and Pearson and Fisher and the people who developed this technology. And the question was, did it make sense to test a hypothesis without any reference to some alternative? That was a point of view that Fisher pushed, and I think it's widely recognized that Fisher basically was wrong. To give meaning to a statistical test of H0, you have to, or to make it a useful concept, there has to be some reference to alternative hypotheses. And here's roughly what Fisher was trying to argue. He said, look, suppose that here's the probability for the data under the null. So suppose this is f of x given h0. And so Fisher would argue, look, come on, look at this thing. It basically tells you that the x values are usually low. All right? So if you see an x value that's high, then clearly that's bad as far as the predictions of this hypothesis are concerned. So Fisher would just say, look, take the critical region to be like that, and it's just obvious, is it not, that if you get an x value that's here, then that is uncharacteristic of the predictions of this hypothesis, and so therefore you should reject it. Right? But what if the only conceivable alternative to H0, hang on, let me draw it better, draw it down here. What if the only conceivable alternative to H0 looked like this? All right. Suppose that was the alternative that you really thought, if H0 is not true, then it's going to have to be like that. And now suddenly I tell you that you got a data point over here, and I say, oh, hang on, do you really want to say that this data point was so uncharacteristic of this hypothesis? Actually, it's plausible, at least for this hypothesis, whereas under the assumption of H1, it's completely out of the question. And so then you would say, actually, the data prefers H0 over H1. So what you want to do in this case, suppose this was the relevant alternative, where would you place the critical region? You would place it on the left, right? You would say, well, actually, if you got a value, maybe this shoots way up to infinity, say, and so maybe we put the critical region just here so that you get your alpha probability there, because if you see the data value here, sure, of course, it could have been that the hypothesis H0 is true, but that region over here is much, much more characteristic of the alternative. Yes? Ah, well, that means that the true hypothesis is perhaps some... So let's suppose that you only have this. We're back with Fisher, so to speak, and I want to make sure I don't say something that's incorrect here, because it seems natural from the way you're posing the question that surely if you say that this is the only hypothesis that I want to talk about now, and then I look at values of x and I see somehow that they're all very high, then I think what you would naturally assume is that there must indeed be an alternative hypothesis that predicts a high probability for high values of x. So somehow I think what you would be naturally led to is well, but if you rejected the null hypothesis, then what you're doing implicitly is you're saying that those x values are incompatible with H0, and in saying so, what does that mean, incompatible with H0? That means more compatible with something else. And the something else would be a hypothesis that predicts probability for higher values of x. So no, you haven't formally written down the hypothesis H1, but what you would have in mind if you want to say values here are uncharacteristic of H0. What does that mean? Implicitly you're saying more characteristic for something else, for some alternative. Yeah.
So when we test a standard model based on that philosophy, so we don't actually say let's test some BSM model necessarily. We can just measure some coupling in the standard model and that's it. But you're saying that implicitly we are assuming that there is some alternative theory, so it gives you different coupling. So even if we don't say the word BSM inside the paper, we're still implicitly assuming that
you're assuming that in the case of measuring couplings and observing values that disagree with the standard model values, implicitly what we're saying is that there could be some alternative that would lead to different effective couplings.
But yeah. That seems somewhat trivial, but I agree with that point. I mean, like of course, if you have some hypothesis with H0, you have the possibility there's some other hypothesis that exists.
Yes. So as soon as you write down a critical region, right, then and you maintain that that is a useful critical region to use, then what implicitly you're saying, and I think this was Neyman and Pearson's point in their argument with Fisher, is that they're saying that you are implicitly saying that that critical region would have a higher probability for some relevant alternative, even if you don't explicitly write down what that alternative is. Yeah. Well, it's not a simple hypothesis because the H0 bar is not a rule that provides probability for data. It's a big family of alternatives.
Yeah, but if you find just like we were discussing before, if you find many X's, very large X's, you say that probably the H0 bar is something.
No, but H0 bar is not well defined. H0 bar is not a unique rule. H0 bar is a large family of potential rules. And it boils down to this type of thing where we'll see this problem come up if you want to test the hypothesized value of a parameter, say. And if you want to say that the alternatives to that value could be higher values or lower values. And that will determine whether or not you come up with, say, an upper limit on a parameter or a lower limit on a parameter. So, or maybe some sort of a two-sided confidence interval that brackets that parameter. So the type of result that you achieve at the end of the day will depend on what you deem to be the relevant alternative. I think this will become clearer as we go along. But I'm glad that people somehow, maybe it's because I didn't explain it well and so there's lots of questions, but I hope it's more just that you want to understand this point, which is good. I should say it is a point that, that people struggled with for many years. Like I say, that especially in the 1920s or 30s, that there were big debates as to the role of the alternative in statistical tests. Yes?
So, for example, if we have a model, like a standard model, and this predicts a certain curve for a certain set of data, then we make experiments and we find a discrepancy in this curve. We cannot say anything without having a second hypothesis. We always have to work with these.
It's implicit. As soon as you write down, you don't have to write down that alternative hypothesis explicitly, right? But nevertheless, as soon as you write down a statistical test and you say, I'm going to use this test to test my standard model, say, there is implicitly behind the scenes an alternative. I'm going to show some examples. I will show examples that will illustrate how one sometimes has to make a choice. And that choice, for example, could result in arriving at an upper limit on a parameter or a lower limit on a parameter, or perhaps some sort of a what we call a central confidence interval for a parameter. Yes?
Just to be sure, here when you say we make a measurement and get X,
Yes?
this is not one measurement.
It is one measurement. It is, yes.
We would reject the hypothesis on one measurement. One collision at the X.
Wow. Well, but as a special case, the dimensionality of the data space could be one. And so just to illustrate that point, it's easier to graph one dimension. So I say one.
We don't collide like two protons. We take one measurement and collide.
No. But nevertheless, very often we take the data from billions of proton collisions, and you might condense that down to a single test statistic. And I might not call it X. I would call it, some letter for a test statistic. But very often you would reduce the very large number of raw data values down to a single number, and you would use that single number to test the validity of the standard model or some other thing. So actually having a one-dimensional axis here is not unrealistic. This comes up. This could be a it could be a function of some other thing, and the dimensionality of that could be a billion. Okay, I think I should go on. I see on my next page what I wanted to do was to sort of more philosophical discussion of this, and this is going to generate more discussion, so good. It was Neyman and Pearson who finally, like I say, won the debate, and they created the language that's used with this theory. And in particular, they say that if the data lands in the critical region, that you reject the null hypothesis. And I want to pause a moment and discuss the meaning of the word reject. Would you agree or not that reject H0, does that imply or not that I believe H0 is false? I mean, clearly, if you think of the vocabulary, they could have just labeled it, outcome 1 and outcome 2 or something. They didn't have to use the words accept and reject, but they did. And this is clearly what they had in mind, is that if you reject H0, you believe it to be false. So what do you think? So strictly speaking, this statement here means something like the probability of the hypothesis is low. Your degree of, I've used the word belief, right? Your degree of belief in the validity of the hypothesis is low. But remember that in frequentist statistics, we don't define a probability of something unless that something labels the outcome of a repeatable experiment. And something like standard model or SUSY is not in that class. If you wanted to actually make this statement with the word degree of belief, you would have to use Bayes' theorem. So Bayes' theorem would say that the degree of belief in that hypothesis, given that you have had some data outcome, this is going to be given by the probability for the data given the hypothesis times the prior probability for the hypothesis, and then you have to normalize that. Let me assume that H is a continuous label, so I integrate, say, or maybe you sum if it's discrete. But the point is that a statement about the degree of belief for a hypothesis necessarily requires that you insert into the calculation your prior degree of belief. So it needs the prior. Whereas yes. Sorry, say, so X is the outcome of the experiment. Yeah. Yeah, so let's suppose that in a frequentist test, that is the X that landed in a critical region, and it caused you to reject H0. Right? So because this X wound up in the critical region. Does that imply, is the question I'm asking, that you necessarily believe the probability of H0 to be low? And what I want to point out is it might or it might not, depending on, among other things, the prior probability that you would assign to the hypothesis. All right? So in the Bayesian framework, you need to supply these prior probabilities. In the frequentist test that I've just defined, there is no prior. But you have, in some sense, the thing that corresponds to that is the fact that the alternative hypotheses are motivating where to put the critical region. All right, so the fact that you do have to consider other hypotheses and where they predict the data to be, that does implicitly enter into the frequentist framework as well. Okay, so that's just slightly more on the same discussion that we've been having, but I wanted to point out that this word reject, even though in the English language it tends to mean I don't believe it, but strictly speaking in the framework of the theories that we've been talking about, it doesn't have to mean that you reject, that you believe the hypothesis to be false. Yes? The theorem itself is a mathematical theorem. There's no debate over that, yes. Well, so the frequentist might argue that the Bayesian approach is maybe problematic because you don't want to associate a degree of belief with a hypothesis. You would prefer to somehow work in a framework that doesn't require these prior probabilities, because the Bayesian framework does not supply any golden rule for assigning those prior probabilities. That's the problematic point of Bayesian statistics. Yeah, it's not the theorem, it's whether you deem subjective probability to be a useful ingredient in a scientific analysis. Yeah. All right, so good, let's go on. So it turns out that if you want to focus on a particular null hypothesis to test and a particular alternative, that there is a well-defined best critical region. So optimal choice of critical region. And this is given by something called the Neyman-Pearson lemma. And so what we do is we consider, for example, some data space. Let me call that S for sample space. That's the notation we were using earlier. And so I have this critical region W. And it's defined by the standard property that we said. The probability to find the data there under the null is, let me suppose it's equal to alpha. So I have continuous data. I'm not worried about this less than or equal to alpha business. All right? Now, let me suppose that for all, I better come over here because this is going to get long. I want to also consider a particular alternative. Consider specific H1. And I'm going to suppose that for all x in the critical region, suppose for all x in W, that the following ratio is greater than a given constant. So the ratio is the following. It's the probability to find the data given H1. So the probability for any point in X space given H1 divided by the probability for that point under H0. That ratio is called the likelihood ratio. For obvious reasons, it's the ratio of two likelihoods. And I want to suppose that for every x point in the critical region, that this ratio is greater than or equal to some constant. Now the constant that I choose will depend on the size of the test alpha, so I'm going to put a subscript alpha to indicate that. So I'll say constant that depends on alpha. All right, so that's true for every x inside the critical region, and the same ratio is less than that constant for x, how shall I write this, not in W. What's the set theory thing? That's something like that. I don't know. Not sure the notation. All right, so basically for every point in x outside the critical region, this likelihood ratio is less than this constant, and it's greater than the constant everywhere inside. And on the boundary, it's equal to the constant if you want. And I claim is that such a region, this region, gives the best test. And I need to say what do I mean by best? And best in this context means highest power with respect to H1 for a test of H0 with size alpha. So whenever you say it gives the optimal test to the best test, you have to specify, precisely what does that mean, best. And this is what my version of best means. It means highest power for a test of a given size. Right. And that's the statement of the Neyman-Pearson lemma. And I'm not going to prove it, but I can motivate kind of how the proof works. And it's not that difficult, in fact, to prove, but we just don't have time. And what you can do is the following, is that if you consider this critical region, and suppose you did the following. Suppose you modified. Suppose this critical region satisfies this criterion here that I've said. Right? And what you do is you modify the critical region by, say, adding on a piece to it here. Let me call that delta W plus, because I'm going to add it on. But I want a test still of the same size alpha. So if there's a certain probability to be in here, then the probability content of the new blob would no longer be alpha unless I subtract off somewhere else. So let me call that W delta W minus. And what you can show is that because when you include this region here, you're going outside the original critical region. And so therefore you're going into a region where this likelihood ratio is lower. And then you're losing something that was inside the original critical region. And in that part, the part that you're losing had a higher value of the likelihood ratio. And as a result, when you work out the mathematics, it turns out that the new critical region always has a lower power with respect to H1. You can almost kind of just see that by looking at the picture. But it turns out to be true. So that's the Neyman-Pearson lemma. Now, okay, so it looks like fine. As long as I specify what the null hypothesis is and what the most relevant alternative is, I have a well-defined critical region. I want to then talk a little bit about, just briefly, how to set a critical region in multivariate problems and why it is that, that this Neyman-Pearson lemma isn't always of such practical value in real problems. You might think that, okay, well, the problem's solved. We have a theorem that gives us the best test. It turns out that in practice, it's not that simple. So this is something that in the discussion sessions, I think in one of the two, I might have started talking about this slightly. So apologies for any repetition. But I want to say this now a little bit more carefully. So very often the type of statistical test that we're trying to carry out has to do with looking for events of a certain type. So let me suppose that I have a multi-dimensional data space now. And so I'll label just two axes symbolically as xi and xj. And let me suppose that I use the colored chalk like I did yesterday. This is good. Let's suppose that the events according to one hypothesis would appear in this space according to some distribution, maybe looking like that. So this could be, that scatter plot denotes the PDF of x given h0. All right? And I want to know, I want to say carry out a statistical test for each event. And I want to know, is it really of type h0 or can I reject the hypothesis of h0? And maybe the alternative to being of type h0 is to be of type h1. And maybe it's more like this. There's some overlap, obviously. And, sorry, I'll label this. So the x's are f of x given h1. And so what's the optimal critical region? So best critical region for a test of h0. And I want it to be best in the sense that I want it to have a high power with respect to the alternative of h1. I want to maximize my probability to reject h0 if the hypothesis h1 is actually true. And so in particle physics, very often what you do is a so-called cut and count experiment. So you would say, all right, I'm going to make a cut on the variable xi. I'll require that xi be less than some constant. I'll call it c sub I. Right? And then maybe similarly with, so which axis was that? That's j. That's I. Then for xi, you do the same thing. So you make some sort of a rectangular boundary for your critical region. I could set the values of these cuts to have a test of a given size, say 5% or what have you. If you look at the way that I've drawn these dots, you might think, well, there's no particular reason to believe that the rectangular boundary is optimal in the sense that I've said, and it's certainly even not the simplest thing. Maybe you would like to have some sort of a linear boundary. Or maybe if you really want to exploit all of the nonlinear features here, let me try to draw the red guys so that they're slightly banana-shaped, okay? And you say, well, I should then make the boundary such that it exploits all of the nonlinear features of these densities and maybe have some complicated nonlinear shape. So which one is best? And, okay, so what we can do is how do we define a surface? How do we define the boundary of the critical region in this n-dimensional space? What you do is you form a function of x vector, and you set that equal to a constant. I'll call that constant t sub c for cut or constant. All right? So that is the equation of a surface in this n-dimensional space. And so all I have to do is to find the appropriate function that gives me the best surface. And then what I would do is, of course, if you look at a particular point in X space, that would give you a value of t, and that would correspond to being on the one side of the surface if it's greater than t sub c, and on the other side of the surface if it's less. And so if you would look, for example, at the distribution of this statistic t of x, then it might somehow end up looking like that for the h0 events. Call it f of t given h0. And something like that for the h1 events. F of t given h1. And so the constant that you set to get a particular surface would then correspond to a particular cut in this one-dimensional problem now for the statistic t of x. And I've basically now said what the optimal functional form of this statistic t of x is, namely it's given by the likelihood ratio. So the optimal t of x is just going to be p of x given h1 divided by p of x given h0. Right? Because that way, if you use that as the boundary of your critical region, then on one side of the critical region, the likelihood ratio will be greater than some constant, and outside the critical region, it will everywhere be less. And so it looks like we're done. It looks like once you specify the standard model and the alternative that you're interested in, you simply write down the statistic, and then you can decide whether an event is best classed as a standard model event or a non-standard model event, say. That turns out to be not useful in practice. So not useful in practice. Why? I mean, after all, if I specify the standard model, I write down the Lagrangian. It's a perfectly well-defined theory, and that means that it has to specify the probability for my data outcomes under assumption of the standard model. So I should have this, right? If you write down your BSM theory, it's fully specified. You can then determine the probability for the data under assumption of the alternative. Why can't I use this? And the answer is just because of our inability to numerically compute these probabilities. So we don't have, in general, formulas for those probabilities. What you have instead are Monte Carlo programs. You have Herwig and Pythia and various MC at NLO and this and that. And so what you have, what you have is the means to say generate points in X space that follow the standard model process. So I could get a set of Monte Carlo events. And I could do the same thing for the alternative process, the BSM process. And so I can have simulated data. Right? So I have instances of points in X space that were generated according to the different models. But now suppose I go and measure a real event from a real experiment, and I don't know whether it was created by a standard model process or by some other process. And I want to know then, for that point in X space, what's the value of this probability in the numerator? I don't have the formula. Right? You can't reverse engineer that back through the Monte Carlo to tell you what the probability was. Right? So that's the difficulty there. And so what you would like to do instead is to write down some ansatz. How shall I write this? So we need an ansatz for t of x, for this test statistic, the thing that's going to define the boundary of the critical region. And maybe this thing contains some adjustable parameters. And what I can then do is I can use the simulated data from my Monte Carlo programs to determine the optimal values of those parameters. And here's now is a big industry of techniques that help you do that. Yes?
I was just going to double check that I understand the logic of what's going on. So you have a bunch of data points predicted by...
Well, hang on. No, I don't think I said that. you have two theories, H0 and H1. This is standard model, that's Susie. Okay.
So now you're trying to draw a critical region to separate these two theories.
Yes.
So you draw a critical region where you basically say Susie always lives here and Stamol rarely.
Well, I don't want to use the word always because, yeah, so in other words, in this data space, xi, xj, there's a surface in that space, and what I want to say is that one of the two theories is largely concentrated over here, and the other one is largely concentrated over there, but they're not completely separated.
You draw this critical region to try and find out. And this is before you've done your experiment?
Yes, that's right. And then what I'm going to do is I'm going to measure a single point. Right, where'd it go? Yeah, and I rejected H0. You can understand this. It's actually, there's two related problems. I don't want to mix these problems up now because this is complicated enough. Maybe it's easier to understand in terms of an event-by-event classification. So I'm not going to, suppose I want to decide whether an event is a TT bar event or a non-TT bar event. All right, so I know that the TT bar process exists. I know that backgrounds exist. So I look at each individual event and I want to select the event, say, for further study. Right? And so I measure the event. It falls on one or the other side of the boundary. If it falls on the side which is more characteristic for TT bar, I keep it, and so forth. Yeah.
So I looked at how you generated the data point.
With a bunch of Monte Carlo models. In some other fields, you can play these similar games with the simulated data is what I'm going to call training data. Because these are the data points that you use to determine the parameters in the thing that controls the shape of the surface. Right? And in particle physics, inevitably, this relies on Monte Carlo data, because there you know that you're running a Monte Carlo program that simulates standard model process. You're running the Monte Carlo program that simulates SUSY. So you know whether you're using this guy or this guy. Right? But if you had real data, then of course you wouldn't know a priori, is this a TT bar event or a QCD event? Well, I'm talking really here about the frequentist approach, and what I'm trying to do is define the critical region of a test. So that is, yes, that is before I would look at the real data.
Right, so this is almost like, not exactly, but it's kind of similar to the prior in the Bayesian approach. You're coming up with, before you have the data, you're coming up with something saying it's likely to be here and not likely to be somewhere else.
Yes, but what I'm doing in contrast to the Bayesian approach is I'm not saying a priori that I think that this hypothesis is a priori more likely than that hypothesis.
Okay.
All right?
But in both cases, you're drawing region.
Let's not go to the Bayesian case yet. All right? Let's just focus on the frequentist problem. Yeah.
So just to be clear, I mean, initially you were saying that that the name system was not practically useful because you don't know.
I don't have these formulas. If you give me an X.
You do by Monte Carlo, right? Monte Carlo gives you those formulas.
No, Matty, it does not. I mean, the way that you generate, for example, a point in X space according to the Monte Carlo, it goes through many, many stages where at the end of the day, what pops out is a value of X which follows this probability distribution. But I don't know the probability of that specific point. I don't know the value of this function.
But you can build that function. I don't think I mean, even if you simulate every process, there exists an infinite amount of
So so why can't I reconstruct? All right. Let's do this carefully. You might say, all right. Suppose I wanted to know the thing in the numerator. Okay, the probability of x given h1, and let's suppose that x is a single-dimensional thing. So let's suppose that it's just a single value of x, and what I could do is I could generate many events, and I could construct the histogram. Okay, and so I get something that looks like the PDF of x. All right? And now I come along with my real data, and I get an actual observed value of x here. And I could say, all right, fine, I simply use the envelope of the histogram as the proxy for the probability. And that would be fine in one dimension. Right? Now, of course, there is a bit of a problem in the fact that you have to have enough Monte Carlo events to do this. Right? Now, let's suppose it's 2 dimensions. All right? All right, so you fill this point with the space with points, and then analogous to estimating the probability here, I count up the number of points in this cell here, and I use that for my approximate estimate of the probability to be at an xi and xj value close to that cell. All right, now I come up with a real data point, and I want to know what's the probability here. I say, well, actually, I didn't generate enough Monte Carlo events to get many points in there, so I don't know the probability. So okay, fine, you generate more Monte Carlo events. But if you look, the number of events that you would have to generate to populate each cell in this space with, say, enough events to adequately estimate a probability there, that grows exponentially with the number of dimensions in the space. The number of events you would have to generate grows exponentially with the number of dimensions in the space. So this sort of technique of using a histogram as a proxy for the probability, that's fine in one dimension. It might even work in 2 dimensions, but for higher numbers of dimensions, it basically doesn't work. And certainly in the types of dimensions that we're dealing with, which is like 20 dimensions or 100 dimensions, it's right out. Yeah.
So it's really practically
That's correct. That's correct. There's no. It is a bit mysterious because you're saying, hang on, it's a perfectly well-defined theory. That once I fix what I mean by the standard model, this formula has to be known. But in practical terms, it's not known. Okay. Yeah. Okay. So I just wanted to mention this other thing that we use Monte Carlo data. And we can't use real data because when you look at real data, there's no way of knowing on an event-by-event basis really what it was. But suppose you wanted to use this type of thing to classify fish, right? So you're all industrial fishermen. You have some big fishing boat, right? So you cast your net, and these fish run up on the conveyor belt. And at first you hire cheap labor to do this, right? And they look and they say, cod, sea bass, cod. And they classify each of the fish. But then you want to replace that worker by a computer, right, that takes a photograph of each fish on the conveyor belt going by and measures a point in X space, which could mean its mass, its length, spectral reflectivity of its gills, and so forth. And so you get some vector of numbers, and on the basis of those numbers, you want to decide whether the fish was of one type or another. And so the question is, what would you use as training data? Well, you go back to the cheap labor. Okay, you get the fellow to actually give you a sample of fish of one type and fish of another type. And so the training samples in those cases could, in fact, in principle, be based on real data. But in the particle physics example, we can't do that. Okay. All right, let's go on. I did want to make just one quick comment about what kind of ansatz could you make. Just an example. So I want an assumption for the form of this test statistic that contains a smaller number of parameters. This brute force approach that I just mentioned, suppose you wanted to have a histogram, an n-dimensional histogram with m cells per dimension, and I had n dimensions, then you would have m to the n cells, which would be that number of parameters to determine. So with this is with a histogram, an ND histogram with m bins for each dimension. All right, so there you would have a very large number of values, parameters that you would have to determine with the training data. I want to make a proposal for the functional form of this statistic that contains far fewer parameters, fewer than this m to the n. And one thing that you could try would be a linear ansatz, linear test statistic. You could say that let me suppose that t of x is just a linear combination of the input values, the x values, so some coefficients ai times xi. And so here, if I had n variables, then I only have n numbers that I need to determine. So if you do this, this is what's called a Fisher discriminant. And And what it results in, of course, because that's a linear function of the x values, the boundary of the critical region will just be a hyperplane, will just be a linear surface in the x space. And on the other hand, if you have some sort of nonlinear features, then you want to have the possibility of a nonlinear surface. So this is going to be linear. And there are various methods that can produce a nonlinear surface. And I'll just list a couple of them. One is called a neural network. There are other. This is something that I'm sure that you're familiar with, but that is basically, from the standpoint of what we've been describing, it is a particular formulation that allows us to describe a nonlinear surface in this multidimensional space. So neural networks. Then there are other things called boosted decision trees. Or BDTs. Support vector machines is another example, SVMs. So these are all things that have been taken from computer science, and in particular the branch of computer science called machine learning. And so the vocabulary very often then leans on that field for the terminology. But in any case, this is a big industry, and it's a topic unto itself. If you look at the lectures that I have on the course page that I referred to, I think it's in lecture 3, or well, you check. It's either, there's only 5 files, and I think it's in the 3rd one. There's some more discussion on these types of things, particularly on neural networks and boosted decision trees, and also I should point this out. Yeah, that archives, and these are the write-ups from CERN summer schools, and both of those two things there also contain kind of a gentle introduction to these types of applications. Yes?
So X is going to be like, let's say, PT of one lepton.
Yeah, X sub 1 could be the PT of the first lepton, X2 could be the missing energy, and so forth.
AIs determine the importance of each variable? Is that not correct?
Well, so let's think about it. If you go back to the I'm tempted to just say yes, but more specifically, if here I just consider 2 dimensions, xi versus xj, I didn't actually write down the criterion that I would use to determine the AIs, right, yet, but suppose that, here was the points. That thing is always going to be a surface. Right? And so if you change the AIs, what you're doing is you're changing the orientation of the surface. And basically what was done is the following by Fisher. Fisher said, define a quantity which is the measure of the separation between the distribution of T under the 2 hypotheses. So remember this picture that if I look at the distribution of T under the 2 hypotheses, they'll have some separation like that. And what I want to do is I want to adjust the AIs so that they are as separate as possible. But I have to define what separate means. Because, for example, what does that mean? Just the difference between the mean values? Well, certainly. But on the other hand, suppose I could tweak the AIs in such a way that the difference between the peak values increased a little bit, but as a result, they became much broader. Okay? That wouldn't be good. Because not only do you want the means to be separated, you want each hypothesis to be tightly distributed about its own mean. And so what Fisher said is he said, look, take the variances. Variance of T given H0 plus variance of T given H1. So that's one possible way of defining what you mean by the separation between these 2 distributions, and it's what Fisher draws. That's what leads to the Fisher discriminant. Right? That's not the unique linear boundary, but that's what goes into a Fisher discriminant.
Sorry, the Fisher discriminant is just the linear hypothesis.
No. It's the linear hypothesis plus this definition for determining the coefficients.
So like minimizing that function is what tells you what AI is.
You want to maximize that function. Yeah. Yeah.
So you don't have to reduce like the area of the flat.
No, that would be another criterion that you could use, but that would be different. Yeah. How are we doing on time? And do we? So I should stop by quarter two. Is that right? Yeah. Okay. Good. Now that's just about right. How are people doing in terms of sort of their internal energy? Are we okay? I'm going to pause for a minute. We're good. I think we better not take a break now, or else we won't complete. All right. Let's go on and define now another very important topic, concept, and that is the concept of a p-value. Well, let's see, before we leave this business of defining a critical region and using the different types of test statistics, I just want to emphasize that this is something that we could spend, several lectures just talking about this. It's not very well, it doesn't lend itself very well to working on the board because it's a lot of computer science, but if you look at those two papers that I referred to in the set of lecture notes, there's a lot of additional information there. And very often this is the type of jargon that you will hear coming out of experimental descriptions. They'll say, oh, we used this or that neural net, this or that BDT, and so that's the basic idea. These are all different prescriptions for determining the test statistic that separates the event classes. Yeah.
Is there a way to show this is a good way to minimize, to satisfy the Navier-Pearson lemma? Or is that not?
All of these things, at the best, what happens very often, I've told you that there is a best possible answer, and that's the Neyman-Pearson lemma. And so what you can do is when you look at the performance of a neural network versus a boosted decision tree versus an SVM, you'll find that they all kind of saturate at some performance. And of course what's happening is they're coming up to the optimal performance. Yeah. We had a competition that ran in 2014 called the Higgs Machine Learning Challenge. If you Google for that, you will find a competition that was hosted by this company called Kaggle. Kaggle provides a web platform for these types of competitions. And what we did is we put some simulated Higgs data from Atlas onto the web there and some simulated background events. And we invited the participants in this competition to come up with the best possible separator in, like, I think it was a 36-dimensional space. And there was real prize money. It was like 10,000 euros. No, sorry, dollars. It was a US based. Anyway, I think the first prize was $7,000 or something. And what we found was that all of the top competitors got very, very close to this optimum. Right, so. All right, let's go on. And this is now another very important topic. And that has to do with testing significance, or what I'll call goodness of fit. What we'll see is it's really just a reformulation of the same concepts, but it introduces this idea of a p-value, which is very important. So let me suppose that hypothesis H gives some probability for some data. All right, and I'm going to suppress the subscript now because I'm going to pretend that I don't have to think about an alternative. All right, and so now I've got this data space. All right. Once again, I'll say this is a xj versus xi, right? And so this rule predicts some density on this space. And then the outcome of my experiment is going to be a single point. Watch this. Boom, there it is. Single point, x observed. And on the basis of that single point, I now don't just want to make a binary decision, accept or reject. I want to give a numerical value that somehow quantifies the level of agreement between that observation and the predictions of that hypothesis. So I want to actually get a number out now. Now the way that we can do this is the following. Is what the analyst has to introduce into the problem is a boundary. And I'll write it here. And it's going to be analogous to the critical region, but it's not going to be quite the same thing, because it's going to pass through and include the observed point. And what the analyst, and this is not going to be a linear boundary in general, it can have a complicated shape. Right? And what I want to do is I want to say that on one side of the boundary, the outcomes here represent less agreement, less compatibility with the predictions of the hypothesis. So you can imagine that in this case, I would get a high density over here and a low density over here. And so this, I would say, I'm going to label this omega with a little less than or equals sign. And that less than or equal means X has equal or less compatibility with H. Sorry, my compatibility with the predictions of H. All right? Which is to say that over here on this side of the boundary, I'll call that omega greater than, okay? And this gives greater compatibility with the predictions of H. And this is not unique, and it has to be introduced by the analyst. That is to say that this is an additional input that has to be made. And so, of course, if you think about the discussion that we've just had in the last hour, what does it mean for a point here to be less compatible with H? Implicitly, what I must have in mind is that it's more compatible with something else. So less compatible with H, I will say, has to mean, i.e., more compatible with some alternative. But in the formalism that I'm describing, you don't necessarily have to write down explicitly that alternative. Right here, I don't need that line. Right? Then, page out of order. Phew. Good. What I define is the p-value of the hypothesis is simply the probability to find the data in this region of less than or equal compatibility. And that, of course, depends on the observed value of x, because if I were to, that boundary always includes the observed point. Right, so what the analyst has to specify is not only where is this region for that specific observation, but there has to be a recipe that would tell where that boundary lies for any possible observation. So you can imagine there would be a family of curves that, depending on where the observed point lies, that boundary would move around. All right, and so the p-value of the hypothesis is then defined to be the probability to find the data point in the region of less than or equal compatibility under assumption of that hypothesis. Right, and that's the p-value. And so what's the basic idea? The basic idea is that if there's only suppose this number comes out small. So say if the p-value is small, that means that there's only a small probability to get data with even worse compatibility. Right? For even worse compatibility. And so therefore you would say something like, well, therefore the hypothesis must have some problem. It must be bad. It must not predict well. It must not be in good agreement with the data that I've observed. And so therefore you might think, small p-value means hypothesis bad. Does that then mean that this is equal to the probability of the hypothesis? Obviously no. Right? If I wanted the probability of the hypothesis, I would have to be Bayesian. I would have to use Bayes' theorem, and that would necessarily require a prior. So if you want the probability of the hypothesis, given that you observe this point x, you would have to say that that's proportional to the probability to observe x given h times some prior for h. All right? But we don't have this in the game that we're playing. This is a frequentist construction for the p-value. And if you wanted to do the Bayesian approach, you'd have to supply the prior, and then you could say that the result is equal to this posterior probability. The p-value is simply not the same thing. It's the probability under the assumption of h to get data at least as bizarre as the data that you found, or more so. Or by bizarre, I mean incompatible. Okay, good. That's going to need more board space, so I better erase this. Yes, you can, because that's the next thing that's coming up. You can imagine, suppose that the hypothesis is true, and you were to observe many times this point in X space, and you were to get a p-value each time. What would be the distribution of those p-values? And it's quite easy to show. I'm running out of longer pieces of chalk, but I see we have a huge number of... I'm good here. Even more, right. Right, I see it now. Yeah. So exactly to this question of what would the typical p-value be under the assumption that the hypothesis is correct, what you can show quite easily, I won't show it here, but I'll maybe leave it as an exercise, is that you can show that the PDF of the p-value, under the assumption that the hypothesis it refers to is the relevant one, it's uniformly distributed between 0 and 1. Okay. On the other hand, if I've defined the p-value in such a way that, here I'll draw it here. Suppose I were to look at the PDF of the p-value under the assumption of some alternate hypothesis h prime, you might wind up with something like this. All right? That you would typically get, say, low values as the p-value of h if h prime is true. Now, under what circumstances would this happen? This would happen if you take the region of less than or equal compatibility for h to actually represent a high probability under assumption of h prime. So that if you were generating the data under the assumption of h prime, you would very often wind up in that region of low compatibility for h, and you would very often therefore get low p-values. All right, so that would be a typical situation. All right, but now given this situation, given that you have a uniform distribution for the p-value under the assumption of h, I can use this p-value to define a critical region of a test. So I can wed this concept of a p-value with the types of tests that we were talking about in the first hour. And that's very easy to do. Sorry, let me just redraw this again. So suppose we have f of the p-value given h, and it's uniform from 0 to 1. And now I consider a particular test size alpha, and I ask what's the probability to find the p-value less than alpha. So the probability to find, how shall I write this? The p-value of h less than alpha given h. That's just alpha, that's just the probability to be over here, and so that is equal to alpha. Right? So I can use this as the definition of a critical region. So I can use that criterion to define a critical region W. I can say that W is going to be equal to the set of X space such that the p-value, I'm going to call this, for example, I'm going to call this hypothesis H0, okay? And I will call the corresponding p-value P0, because that subscript labels the hypothesis that it's the p-value for. It's so the critical region is the set of X space that would result in a p-value, do I want less than or equal to alpha? Voila. So once I've defined a p-value, I could say, look, consider the region of the data space that would result in a p-value less than or equal to alpha. That fulfills the criterion of a critical region. So I can use that to define a critical region. Now, even though I've done this without explicitly mentioning any alternative hypothesis, the resulting critical region, of course, I could use it and I could compute the power of that critical region with respect to this or that alternative. Right? Yes, but here the difference is that what we get is a number that quantifies the degree of compatibility between the hypothesis and the data. So I'm going to get a number, but I will use that number also to define a critical region. So yes, it is exactly the same as what we did before. Okay, now in physics, in particle physics in particular, rather than say that I got a very low p-value, so therefore I reject this or that hypothesis, we convert that p-value to a number called the significance. And I usually use the letter Z for significance, and it's just a one-to-one mapping from the p-value, and here's the recipe. What you do is you take a unit Gaussian. So this is a Gaussian with a mean mu of 0 and a standard deviation sigma of 1. So that's what we call the standard normal distribution, right? And so there's this variable of the Gaussian x. And what I do is I come up some number of standard deviations, so some amount z. So the standard deviation of the curve itself is 1. So I come up z such that the upper tail area in just one direction is equal to the p-value. And so that defines the connection between the significance z and the p-value p. And so the integral from minus infinity up to here, that's the cumulative distribution of the Gaussian. And so this p has to be 1 minus the cumulative distribution. So the p-value is 1 minus, and the notation for the cumulative distribution of a standard Gaussian is usually capital phi. All right? And so, voila. So that's the cumulative distribution of this standard Gaussian. So that's the kind of function, of course, that you have available in computer libraries and so forth. And if you know the p-value and you want to find z, then of course you just take the inverse of the cumulative distribution. So there's 1 minus p. And this inverse of a cumulative distribution is what's called the quantile. And of course, for that as well, there are so quantile of standard Gaussian. There are computer routines as well that will give you the quantile. And so rather than saying, I got a very low p-value, so therefore I reject the hypothesis. Yes? Yes, that's exactly. So that's what I was just about to say, is that one of the ways that you can interpret this z, if you're observing a signal, is that this z turns out to be essentially the estimated size of the signal divided by the standard deviation of the estimate of the signal size. So, in other words, if you found something that was 9 in some units plus or minus 3, that would correspond to a significance z of 3. And so in particle physics, of course, as you know, that very often we would say that you can reject the no signal hypothesis if the significance with which you, if the significance of that is greater than or equal to 5. So z greater than or equal to 5 is somehow taken as discovery. But let's be clear at what you're doing here when you do this. What you're doing is you're testing the hypothesis that there's no signal present. If you can reject that with a sufficiently small p-value or a sufficiently high significance, then if you reject the no signal hypothesis, you can then claim that you found the signal. But z equals 5 corresponds to an incredibly small p-value. It's like 2.9 times 10 to the minus 7. All right, so I think when statisticians look at that very small p-value that we use before we dare to talk about a discovery, they're quite surprised. That's another discussion in itself as to why this 5 sigma threshold in particle physics is used. There's a whole folklore behind that. Maybe sometimes it's well justified, in other cases it's just folklore and maybe less justified. But in the case of many of the discoveries that have been made in recent years, particularly the Higgs discovery, I think upon reflection it was about the right threshold. And it's certainly what's very often used. Okay, so that's that. And now I want to do an example. I think I can do this in 7 minutes almost. Yeah, this is a good place to end. Good example to end with. So here's the prototypical particle physics search for a new process involves the following. So we define a search region and count events. So we're going to count in a search region. So this search region is going to correspond to a critical region of a test. Well, I don't even have to insist on that. I've defined some search region where I think that signal events could be present, and I'm simply going to count the number of events. And the number of events that I count, I will say, is going to follow a Poisson distribution with a mean of S plus B, where S is the expected number of signal events, and B is the expected number of background events. Now, in saying that, what I really mean is that there's going to be a number of signal events, and that itself is going to follow a Poisson distribution with a mean of S, and there will be a number of background events that follows a Poisson distribution with a mean of B, but I don't observe NS or NB separately. So these I don't observe. I only measure their sum. It may not be completely obvious, but it's true that if you have two variables that each follow a Poisson distribution and you construct their sum, the sum also follows a Poisson distribution, and the mean value is equal to the corresponding sum of means. Right? And so that means that what's my law for the probability of the it's Poisson distribution with a mean of S plus B, so I can write this down. Right? And let's suppose that the expected number of background events has been figured out using, say, some Monte Carlo simulations. So suppose B is known, and I'll take 0.5. So for example, from Monte Carlo. Maybe I did this also with some sort of control measurements on a sample where I engineered it so I knew that there was no signal present, it was only background. But in general, there will be some uncertainty on this estimated background rate, but let me suppose that that's negligible. So suppose that B is equal to 0.5, and then you do the experiment, and we find 5 events. Now, before we go through the formalism, what would you tend to think? I expect 0.5 background events, and I saw 5 events. That doesn't seem very compatible, does it? Right? Certainly you think, aha, there must be some alternative, some signal process which is contributing events, and that explains why it is that I get so many, 5. Right? Because the probability for a Poisson distributed variable with a mean of 0.5 to give you that many events is very small. So what I can do to quantify the level of agreement between that observation and this model is to give the p-value of the hypothesis that there is only background. So p-value of the hypothesis that S equals 0, so the background only hypothesis, and I will call that p sub 0. Now, what I have to do in the p-value, remember, is to define the portion of data space that gives me equal or lesser compatibility with this S equals 0 hypothesis. So let me open parenthesis and now leave that blank. The hypothesis is that S is equal to 0 and B is equal to 0.5. I found 5 events. What number of events would constitute even worse agreement with the hypothesis of S equals 0? Well, 6 events, or 7, or 8, or even more. All right? So I would say that this is the probability to find n greater than or equal to 5. But now, in choosing that as the region of lesser or equal compatibility, I'm implicitly saying that there's some alternative to S equals 0 that would give me more events, that would be more compatible with this region, n greater than or equal to 5. And of course, what I'm thinking there is that the alternative to S equals 0 is some signal which would contribute events, so some S greater than 0. That would predict a higher probability for higher values of n, and so therefore I take that to be my region of lesser or equal compatibility with the background-only hypothesis. All right, so if you do this, you get a number. So this is then the sum from n equals 5 to infinity of b to the n factorial e to the minus b, because it's the s equals 0 hypothesis. And there's some numerical tricks that I'm going to give on the problem sheet for this afternoon for computing these kinds of sums that involve, you don't have to sum an infinite number of numbers, that's nice. And when you do these tricks, you get a number here, 1.7 times 10 to the minus 4. And so immediately you're thinking, it's small. Does that mean that the probability of s equals 0 hypothesis is small? No, this is not the same as the probability of the s equals 0 hypothesis, just to say again. Right? This is the probability, assuming the s equals 0 hypothesis, to see data with equal or less compatibility compared to the level that we got with our actual observation. Then, given this p-value, of course, we could convert that to the corresponding significance with the formula that I just gave before, and this turns out to be 3.6. So we would call this a 3.6 sigma effect. Right. I think that's a good place to, I'm not going to go on to this business with interval estimation today. That can wait for tomorrow. But so what would you do with this 3.6 sigma effect? Well, obviously you run to the CERN press office and you say, I have discovered a phenomenon by finding, or maybe it was more than 5, then you go to the CERN press office, right? And the press officer will write up a press release that says, scientists at CERN have found that the probability that the standard model is true with no new process is equal to 1.7 times 10 to the minus 4. And they say, no, you can't write that. That's wrong. Right? The correct sentence is the probability, assuming the standard model, to see data as discrepant as we found, or more so, is 1.7 times 10 to the minus 4. And they go back and forth 1,000 times, and the press officer says, I'm sorry, I can't write that. That's just impossible. And sure enough, if you look at the CERN Courier, the number of times that they have incorrectly interpreted the p-value as the probability that the standard model is true, it's like every time practically. It's a running battle that I have. But, the correct phrase is that this p-value is the probability under the assumption of the background-only hypothesis, which is to say the standard model hypothesis, say, to find data as discrepant as the data we found, or more so. Right. You have to define then what does that mean to have data that's even more discrepant. It's discrepant with the standard model means more signal-like. Okay, I think that's maybe we should declare victory and retreat for today. And we will continue tomorrow.